let's start with a little history of Bash. So Bash was part of the GNU project, written by Brian Fox. Now, Richard Stallman of the GNU project thought that it was really, really important to have a shell that was fully compatible with the Bourne shell. Of course, the vast majority of scripts in the Unix world are written in the Bourne shell at that time. So they actually funded, out of their own foundation's coffers, Brian Fox. They employed him and funded him to work on this project. And it was first released in 1989. And of course, it was a true superset of the Bourne shell. So that's our history lesson. Now, I'm talking about bulletproof, so-called Bash scripting. So what does bulletproof mean? Well, I pulled some words out of a dictionary and kind of threw them up here, and I thought they looked pretty good. Robust, predictable, repeatable, accurate, exacting. And we'll kind of talk about how each of these applies along the way. But, you know, a lot of people, they have this notion about Bash scripts that it's hit or miss, you know. It either works great or it fails miserably and I don't know why it failed. Or it fails miserably and it took me a week to figure out why it failed. Or the user says it fails, but it always works for me. See, these are things that violate this whole idea of bulletproof. If it's predictable, if it's repeatable, it's going to work the same for you. It's going to work the same for your user. It's going to work the same night, noon, morning, whenever. What bulletproof is not. Bulletproof is not secure. They're not the same thing. They're two different worlds, really. So I'm going to just say never make a setuid root bash script. Just don't do it. Just resist the temptation. It's bad. There are too many attack vectors. Clearly there's path, there's LD library path, there's the input field separator, IFS, there's temp file hijacking, and that's just a start. So if I'm on a box and I'm a regular user and I see a setuid bash script, pretty good chance I can get root on that box. So avoid that. That's not what we're here to talk about. We're not here to talk about securing these things. We're talking about making them repeatable, making them robust. So we're going to start with path and UMask. Now, everybody knows about path and UMask, but I'm going to say it just to be complete. You should always set both, in my opinion, and a shorter path is usually better. I see people who make paths 10 miles long, but you know what? I think you need 4. Maybe you need user local bin 2, maybe 5, but usually 4. User bin, user sbin, and sbin. And UMask is a lot less work than doing chmod on everything after the fact. So UMask sets a mask against the default permission. Usually when you create a file, it has a default permission of 666, read, write, read, write, read, write, and then the mask is subtracted from it. So if you subtract 22 from that 666, you get 644, or read, write, read for group, read for other. So UMask it's a lot easier than trying to remember to go back and chmod all the files after the fact. Set-xv. This is where it starts. This is where it starts to get good, in my opinion. Set-xv, a lot of people, they play with it, they turn it on, they think, oh my gosh, what is all this gobbledygook? I can't read this. They turn it off, they walk away, they never look back. That's okay, I can relate to that. I was that guy at one point. But I finally learned to love set-xv. What it does is it prints each line as the bash shell reads it to the standard error. Then, on the next line, it prints a plus sign, and it shows you the final version of that line after variable substitution, after path name expansion, after quoting resolution, word splitting. All of that happens, and then the shell will show you what it's finally going to do. So you get to see kind of the before and after, and that's really helpful in understanding what that shell's doing. Now finally, pipes, shell functions, and redirections, they can be a little non-intuitive. But we're going to have some of those in the examples. So I'm going to point that out to you, and I'm going to say, hey, look, remember when I said non-intuitive? So we'll see that in a minute. Exec to greater than log file. This opens a log file for append, and it redirects the standard error output to this log file. This is going to capture the errors from our programs and the output of the set-xv. All of that's going to go into a file so that we can always have a sort of record after the fact of what the script did, and we can understand it. We can go back and see at each step in the script, what did it do? My typical usage, I use exec 3 greater amper 2, amper $me.log, where me is a variable I've set to the name of my script, and then 2 greater than amper 1. So what this does, this opens file handle 3 as a dupe of the standard error. So I've still got the standard error, even though I'm going to put the standard error output to this file. And it also sends the standard output to this file. So this is going to capture pretty much everything that's going to come out of this script into this file. And if I still want to send an error message to my user, I still have a dupe of standard error on the 3rd file handle that I can do that with. Set-E. Now this is what makes it possible, in my opinion, to have bulletproof bash scripts. Set-E is error checking on steroids. It's error checking built in. It's the shell doing all the error checking for you. What it does is the shell checks the return code of every simple command after it runs it. And if any of these simple commands returns a non-zero error code, the shell exits. So it stops. A lot of times in our bash scripts, the shell goes right along, does whatever we asked it to. It has an error. It doesn't notice the error. I mean, why should it? And it goes right on to the next thing, and it keeps going. And only after the fact, when your shell said it did what you wanted it to do you realize that it missed something along the way. Set-E prevents that from happening. Set-E throws the brakes on the instant you encounter a problem. And this works for the built-ins too, like CD, change directory. Now, sometimes you want to ignore an error. You're really like, I just don't care. You want to make the directory foo. It might already exist. You don't care. The easy way to get set-E to ignore that is to add or and a colon. Colon is the no-op in the shell. Colon does nothing. So you say, make dir foo, and if that fails, do nothing. See, that takes this simple command, make dir foo, and makes it into a complex command. And set-E doesn't check on complex commands. It expects you know what you're doing, right? You made it complex. You must want to handle that error condition yourself. Ad hoc error checks. This is what people normally do, right? People will go into their bash scripts and they will put an if-then around every line, practically, to say, if it didn't do what I wanted it to do, throw some big error message to a log, yell bloody murder, set the fire alarm, do something. The problem with ad hoc error checks, well, there are 4 problems. There are a lot more than these, but these are the ones I threw on the slide. They take time and effort to write, obviously, and they seldom include everything you want to know. How often do you actually see error messages that say what line it failed on? People don't usually do that. It's too much work. They're only added to the places you think are going to fail, which is not usually the places where it does fail, because it's usually the surprises that get you, not what you were expecting to happen. And they can even introduce more bugs. I can't tell you the number of times I've had to debug somebody's error code, somebody's debugging code, and that's just like, okay. Trap, bang, exit. So trap is it's sort of the unexplored wilderness of the shell for most people. Most people don't use traps. Traps let you catch signals, sigint, sighup, all of that. Everything that your normal daemon can get and react to, well, your shell script can get and react to too. But it can also do other things. Trap can handle things like the exit condition. So my usual formula is to put a trap on exit. And I call it bang, just for fun. Because when a machine dies, you want it to go bang, you want to know it happened. You want the blue smoke to rise. You want to know some sort of indication, oh, that one's bad. So I call it bang. So trap, bang, exit here It runs just before bash exits, and bang, in my typical usage, my typical recipes, is a shell function. And I use it to alert me to look at the log file. So all the really good stuff is in the log file. But if it all worked just fine, then I don't need to look at the log file. The log file is going to be full of stuff that was just fine, and I don't need to go look at it. So I want the bang to tell me, hey, look at the log file. Now, to disable a trap, you just trap again, and this time you use dash as the argument. Set dash u. This is a lot like set dash e, but it works for variables. So set dash u treats unset variables as fatal errors. And this is an alternative to supplying defaults for every one of your variables. A lot of times our bash programs fail because one of the variables wasn't set. You end up with a command line that would have done something interesting if that one variable had been set to the right path, but it was empty, and so the whole line failed. This will catch that before running that command. Now this also affects $1 and $2 and whatnot. So if you're going to use positional parameters and you want one of the positional parameters to be optional, you say you want it to be possible to give $2, but not always are you going to give $2 to a given shell function, then you need to use a default there. So like curly brace 2 : dash close curly. flock. Now in the little snippet that I put into the book, which amusingly got mashed up with my other talk here about regular expressions. In the little snippet, I described the traditional cron problem. We all write, well, sysadmins and lots of other people write cron jobs. And we want our cron jobs to run once a day, right? We put it in the cron.daily, and we think that's good enough. Surely, right? It's cron.daily. It's going to run once a day. And then a month or two later, you log into your system, it's completely crawling, it's at a standstill, and you're like, what's going on? And you look at the process table and you see 30 of your cron jobs sitting there chewing up resources, memory, CPU. And they're all running, and it was supposed to run once a day, and it was supposed to finish in a day, and it was supposed to exit. And the next day another one was supposed to run, but what happened? It took longer than a day. The next one started before the last one finished. They started competing with each other for resources or locks or there was some sort of race condition, and next thing you know, you've got 100 of them, and the machine can't do anything at all. flock solves this. flock is exclusive advisory locks. So flock is both a system call and it's a little utility. The little utility that we call from our shell scripts just calls the system call. Now these are, let me explain those two words, exclusive and advisory. Exclusive means only one thing can have the lock at a given time. Now this is as opposed to a shared lock, or read-write locks, where you can have multiple reads and only one write. So exclusive is our typical write lock. Advisory, that's pretty important. Advisory means people can ignore it. An advisory lock only works when everybody's looking at the same lock. It means it only works when the programs cooperate to say, okay, yes, I am going to treat that lock to mean don't do something or do something, and so forth. If you have two different locks and the programs aren't using the same one, well, then they're not agreeing, they're not communicating. So flock is exclusive advisory locks. And I usually use the -in switch for non-blocking. If I don't get the lock, I want my program to exit immediately. And I use it on a file handle opened by bash with that exec syntax. And this is handy because when I open it on a file handle that my script already has open, when the script exits, the file is closed, the file handle is closed. And when the file handle is closed, the lock goes away. So I never have to worry about unlocking. That all happens automatically when the script exits. All right, I think we're just about ready for an example. So you could use an existing one or you can open a new one. And everybody, just to be sure about this syntax, exec is a way you can open a file inside the shell script, and it behaves the same as if you had typed on the command line when you ran the shell script an open bracket into some other file. But you can assign numbers. So in this case, I use the number 4. But let's kind of talk about this real quick. So basically, everything in this script is something we've already just talked about. We have our path and our UMask at the top. We have our exec line to capture the standard error output into a log. We have our set-xveu, so all 4 of them right there in a row, doing all the good things that we want them to do. And this is just very typical for me to throw in date and host name there. I use that because when I look back at this file, I can see when the script started and what box it was running on, and that's handy. And because we're capturing the standard output as well as the standard error into this log, just a simple date command is its output is going to go right to that log file. Next we have good old bang and trap bang for exit. Now here's just a directory. I made this up, cd opt query. Here's our flock line. Here I'm sourcing a file to get some configuration variables. This db log keep and db log pattern are supposed to come from this config file. And then I've got your very traditional find pipe to xargs rm. So this is something any sysadmin might write. I want to find files that are older than some number of days that match some regular expression pattern, and I want to remove them. Finally, I've got trap-exit. So if I get to this point, my script has succeeded. And I'm going to undo my trap so that when the script exits, it'll be silent instead of going, bang, it failed. And then I have an exit 0. So this is a very simple script. Now let's see what happens as I step through. It failed. Well, of course, this is a contrived example, so you knew it was going to fail, right? This is what I want to talk about. I want to talk about how to keep them from failing, or how to figure out why they failed. So if I go back and look at the log file that I captured by virtue of set-xv, I can see the date, I can see the host name. This was a virtual box, so it just had the default host name Ubuntu. I can see, so each of these are the lines as the program read them. This is the xv output. So host name, that's what it read, plus host name, that's what it ran. Bang, this is what it read. Now, when it defines a shell function, it doesn't actually echo that back out. Trap bang exit, read it, ran it. cd/opt query, read that, ran that, and here's our first error, okay? I didn't make opt query intentionally. I wanted it to fail here so I could show you. So this is what that output looks like. It tells me the name of the program, tells me what line it failed, tells me what it was doing, cd/opt/query, and tells me the error message that happened, no such file or directory. So that's a pretty good error message in my opinion. That tells you a lot right there. You know just what went wrong. And of course the bang, because the set-e caused the script to exit at this point, because this returned a non-zero return, and it echoed failed, and that of course got my attention to go look at the log file. Okay, so I'm going to make dir opt query because I really want my program to finish. The next line up here, I do a no op and I redirect it into rm logs, and that's my typical way to truncate a log file. You could rm it. So then I run it again, and of course it fails again because, you know, this is a contrived example. So what happened this time? So here's the same, here's our next set of output, and you can see we got past the cd opt query this time just fine. We even made our lock file just fine. What happened here? It went to source, this opt-etsy rmlogs.conf, and that file didn't exist. And again, it tells us the name of the program, the line on which it failed, and this opt-etsy rmlogs.conf, no such file or directory. So we know just where to look, okay? So I'm going to go and I'm going to empty my log again, and then I put some variables into that file, and I cat it out here just to show, yes, I'm a good boy, I put variables in my file. I say 7 days, and there's a little regular expression to match dump and a few numbers, 3 numbers afterwards. And then I run it, and it says failed 3 times, bang, bang, bang. What is that all about? Okay. Let's see what happened here. Here, we're a little farther down in the log file, and it went to source our rmlogs.conf, and that worked. It got the 2 variables. We can see those here. They're preceded by 2 pluses this time. And then we run our find command. But sure enough, we see unbound variable, and we see it twice. This is the set-u in action. And the reason we're seeing this is because I misspelled the variable names. You know, I put db log keep and it's dbg log keep. So this is you can actually make mistakes like this, and here it is telling me, look, you made a mistake, this is what it is. And the reason we see failed 3 times is because this is a pipe. So the way the shell sets up this pipe, it essentially has a context for each section of this pipeline. And in each one of these contexts, the first being the find part, there was a failure. There was a failure because that variable was unset. In the egrep part, there was a failure because that variable was unset. And in the xargs rm part, there was a failure because rm had no arguments. And we can even see that down here. Here we actually see the capture of rm's error message. Rm, missing operand. Try rm -- help for more information. Who says Unix isn't friendly? So I fixed the problem, right? I went in, I edited the config file, I put the little extra letters in there, I run it one more time, and sure enough, it works just fine. So let's see what the log file looks like when it works just fine. When it works just fine, we see the xargs, the find, and the egrep. Now, you remember when I said it was a little non-intuitive, the way the -xv output looks when we have a pipeline? Well, here's an example, right? You would expect the find to be first, the egrep to be in the middle, and the xargs to be at the end in this output, but that's not what it looks like. And in truth, it doesn't matter. So long as the standard ins and the standard outs are connected correctly by the shell, it could really execute them in any order. And here we see it says removed dump.149, 150, 148, 147, 146, 145. And the reason it says removed is because I put the -v switch on rm. Now, how many people have seen all these verbose switches on things like move and copy and rm, and you think, I'd never use that. I never want to see every file it operated upon. It's going to fill up my screen. Well, finally, you've got an excuse to use those verbose switches. You can actually have your log tell you which files it operated on, and there you've got proof. These are the files it actually operated on. Now, one thing we don't actually know in looking at this output is we don't know what files find saw. We only know what files got removed. And so those are files that find saw that match the egrep regular expression and that then were operated upon by rm. So let's see if we can go a little farther and do something different. What I'm doing here, I'm adding one function. I call it cat2. And you're not going to find this in any man page. This is something I just do because I like it. It's a little Perl one-liner that says print to standard error. And because it's Perl, you can say things in a very short way. So what this does is it takes every line that it reads and it writes one copy to the standard output and one copy to the standard error. Now, why would you want to do that? Well, the reason you'd want to do something like that is you could insert this into the pipeline. The copy of the line that gets written to standard output is going to continue down the pipeline. And the copy that gets written to standard error is going to show up in our nice little log file here, captured for us to inspect later. So this is what happened when I ran it with the cat2. I can see, and I also recreated all of those dummy files. You actually can use T to write to the standard error if you write to /dev/standard error, which is actually a symlink on Linux boxes to proc self fd2. And you need to append, because if you don't append, it's going to truncate your log file. So I've been down this path, can you tell? In my final analysis, after having my log files truncated through missing that part, I find that my little cat2 is a little more simple and easy and doesn't get me into trouble. So here we can see that the cat2 showed us what find output. And then we can see what egrep and rm did. And we can see that there were actually some other files in that output that maybe we wanted to delete, but we didn't delete. Those are the ones named diff.149 and diff.145 and so forth. So sometimes it's useful to see not only what you did, but what you didn't do. So we didn't delete those files. And that's easy to do with this sort of capturing everything kind of approach. Okay, so let me talk about expression in single brackets versus expression in double brackets. So I'm going to tell you, the double square brackets are newer. They are a bash innovation. The single square brackets are actually backwards compatible all the way to the original Bourne shell. So bash has to be a superset of Bourne. So it has to do everything the Bourne shell would do. And the Bourne shell would do these single bracket expressions. But Mr. Fox said we can do better. We can make it better. And he came up with these double square bracket expressions. And there's two differences, two very important differences. The single bracketed version does word splitting and it does path expansion. And I've got some examples to show exactly what that looks like coming up. And the double square bracketed expressions does not do word splitting or path expansion. And frankly, I think that many of the errors in our bash script come from accidental word splitting and path name expansion. So let's see what some of this looks like. Now this is clearly a very contrived example. I've got a variable foo, which is 1, and a variable bar, which is 1 space 2. And if I ask bash to compare foo and bar in a single bracketed expression, I get the error. How many times have we all seen this? Bash, open square bracket, too many arguments. And what do we traditionally do about this problem? We wrap it in quotes. Everybody does that. But that's something that you can forget to do pretty easily. Or you can put it in single quotes and then it doesn't do at all what you thought it was going to do, what you meant for it to do. So yes, you can put it in double quotes and it does work. But you can also use the double bracketed version of this expression, and it works correctly because there's no word splitting going on. That space in the bar doesn't matter because word splitting doesn't happen in the double bracketed comparison. Here I'm showing, this time with the -xv output, I'm showing path name expansion. So I do an ls, and you can see that I've got a directory with half a dozen files. And if I say in a single square bracketed expression, -f dump.151, if we do our single bracketed test on a single file, it works just fine. But if we do our single bracketed test on a file name with a wildcard in it, we again get the infamous too many arguments. And you can see in the -xv output that what the shell actually tried to do was open square bracket -f and then half a dozen files. And that is indeed too many arguments. That's not going to work. If we do it in the double square bracketed expression, the test of a single file works correctly. But if we do it with the wildcard, it doesn't work correctly because there's no path name expansion. What this is actually asking is, does there exist a file that is literally named dump.*? Not, is there a set of files that match dump.something? So this is probably not what you want if you want to work with wildcards. But now let me show you what I traditionally think is a better approach to this problem. Now, you saw me use xargs in my example program, and that comes from a long history of being abused by wildcards. Because you see, wildcards, the shell is really happy to just expand that and expand that and expand that. But on our Linux and Unix environments, any program can only take so many arguments. So if you've got a directory with several thousand files, and we've all done it, right? Directory with several thousand files, and you try an rm star, you're going to get an error because there are too many arguments for rm. So xargs is our traditional answer for that. If you can get those files in a list, say with find, and pipe it into xargs rm, it works just fine. But in the same way, you don't really have to use wildcards to do something like test for the existence of multiple files. you can use something like ls and pipe it to egrep. And that's a very similar thing to what I did in the first script. So here I am, I say ls pipe to egrep caret dump backslash dot. Now that's a regular expression that means the same thing as dump dot star in bash. Okay? So these two are equivalent. I say ls pipe to egrep and that regular expression and echo true. And the ls works, it lists the files, pipes to egrep, we see that egrep does indeed match some things, and we get our echo true. And if we don't actually want to see what egrep saw, if we just want to take its word for it, you can use the -q switch to make egrep quiet. So this ls pipe egrep -q dump dot and echo true is the way I would do this in my scripts, and the way I would suggest you do it in your scripts, because this is going to solve several problems, including your problem with spaces. Word splitting again. Word splitting is one of the biggest problems people encounter in bash shell scripts. Word splitting always happens when you don't want it to happen, and it doesn't always happen when you do want it to happen. So here's a little shell function I threw together to list out the arguments. I call it inargs. And basically it's going to put a number beside each argument that I gave to this shell function. So if I say inargs ABC, I see that there were 3 arguments, 1, 2, and 3, named A, B, and C. But if I quote, and I make that first argument A space B, I've given this shell function 2 arguments. But what do I get on my output? I still get 1, 2, 3. And that's because word splitting occurred. If I do it on the other side and I put B space C in quotes, I again get word splitting. It always looks like 3 arguments. If I give it a single argument, A space B space C, word splitting again occurs, and I get 3 arguments. Now, what can I do to make this better? What can I do to fix this? Stop using $*. $* is just this side of evil. Now, what is good? Double quote $@ double quote. How many people use that? Double quote $@ double quote. Okay, good. We've got some. It's great. You should use it everywhere you'd be tempted to use $*. Use that. What that does, the shell says, I will preserve the quoting and not do word splitting when I'm replacing double quote $& double quote. Now, I've got another slide of this where I turned on the XV output so you could see what this looks like. So here is my bad version again at the top that just uses $*. And you can see that when I hand it A space B as a single argument, you can see what actually happens is the shell runs that little Perl snippet with A, B, and C. But if I do it with my $& in double quotes, what the shell actually runs is this Perl snippet and then preserving the quotes, single quote A space B, single quote C, and we get our desired output, which is 2 arguments, one of them containing the space. So what is this? This is some little improvements. When I wrote that first script to show you guys, I basically based it on a real script I have, but I stripped out some of the things which look kind of like line noise or gobbledygook. And here I'm going to show you some of those back from the original script. What I usually do with my bang, this is a better bang, is I actually test $?. Captures the return code of the last thing to run. And I test it. And if it was equal to 0, I just return inside my little bang. And this time I call it end instead of bang, because if the script exits correctly and successfully, if the last thing to run gave a 0 return code, then I don't need to say failed. It didn't actually fail. So by testing $? To see if it was 0, I can leave this trap in place for the whole script. I don't have to disable the trap. Basically, the trap is smarter. It knows whether or not the script really failed or whether it succeeded. Better bang. Okay, better base name. I don't know how many people actually use Bash's built-in variable editing replacements. But we see things like base name $0, and that's really easy, right? But you can also do that by operating directly upon $0 with a replacement. So this double hash sign says to take this pattern, the longest version of this pattern, and to replace it, or to chop it off. So basically I'm saying everything up to the last slash in the line, throw it away. And that's just what base name does. So this is a way to do base name entirely inside of bash. And once you start doing it, you'll get addicted to it, and you'll be doing all of your replacements inside, and a lot less calls to sed, awk, Perl, base name, what have you. And then a better top directory. So in my script before, I had hard-coded things like opt, /opt/bin, /opt/query, /opt/etc. When I write real scripts, I almost never hard-code those things, because on some boxes I might put a script under op, on other boxes I might put it under user local, on still other boxes, like at work, it'll be /securework/bin or something. So these things can live in multiple places, and the fact is it's really easy to figure out where the script lives, because $0 contains the path to the script. Now it's either the full path to the script, which that's going to be the case if you run the script and the shell has to go search the path to find it and run it for you, then that's when you're going to get the full path to the script in $0. Or it's going to be a relative path to the script. And that's what happens when you say ./bin/foobar. So what I have here is a little test. And this is again using some of Bash's built-in variable manipulations. So what I'm saying here is this actually evaluates to the first character of $0. So I'm asking, is the first character of $0 a slash? If the first character of $0 is a slash, well then I know I've got the full path in $0. So I go ahead and set top to be that full path. If it doesn't start with a slash, I know I've got a relative path. So I set top to be the value of PWD, or the current working directory, followed by $0. And then, again using some of that bash built-in variable replacement, I just strip off the /bin/whatever part of that directory. So in my earlier case where my script was called rmlogs, if I called it /opt/bin/rmlogs, then top would get set initially to opt bin rmlogs, and then it would strip off the bin rmlogs part, and top would be set to opt. And then I could use that variable top and reference all of my subsequent files, like my config files and my log file, relative to that top directory. And that could be opt or user local or, well, anything. All right, so that was the better top. And I put this XKCD up here because this makes me laugh, this part. His blog has 4 posts, all apologies for not posting more. How true is that? How many blogs out there are just, really, I'm going to start writing more, I'm going to start writing more. I love XKCD, Randall's great. I think he speaks to our generation. But that's the end of my talk. Any more questions? Yeah, question.
Is there a difference between bin.sh and bin.bash? Is there often just simple?
That's a good question. Is there a difference between bin.sh and bin.bash? When they're symlinks, they are in fact the same program, but the question would then be, does bash do any POSIX emulation when it notices it's being run as bin.sh instead of bin.bash? I always say bash. I don't want there to be any doubt. I mean, bash really has been around, 20 plus years, right? So, and it's on all distributions, on all Linux distributions, and even on pretty much all Unix distributions.
You will encounter places that don't have bash installed if you venture outside the Linux world.
Well, of course you will. But the first thing you're going to do is install it, for crying out loud. I mean, come on. That takes me way back. I remember the first Unix box I worked on was Sun OS 4. It ran on, actually on the Motorola chip. This was before Sun introduced the Spark chip. They were still selling Motorola chips. And this was multi-user Unix. You know, most people these days, they have Linuxes, they have BSDs, whatnot, and everybody is basically on a single user machine. There's so very few multi-user Unixes in the world anymore. They still can do multi-user, mind you, but nobody uses them for that purpose. So that original sense of community you had, where you had a system administrator who was the only one who had the root password, and you could go pester him for questions like, what does this do? What does that do? That sort of sense of community is actually, it's been lost. And that's kind of a sad thing. But in its place, we have this. We have conferences where we can all get together and have some community again. So that's nice. But I do remember the days when you would run talk on your multi-user Unix box, and you would talk to the sysadmin, and he would talk back, and you could actually get to watch him typo as he, I remember telling somebody, I speak typo. You really don't have to backspace over a whole line just to fix that one letter. All right, so that's all I've got. Any more questions? Okay, thank you, everybody. Thank you for coming.